Tu peux commencer.
Ah, je peux commencer.
Ouais.
Ok.
Attends, on peut juste le foutre en plein écran ou ça marche pas? Là, c'est supposé être. Ah, là, il me considère que c'est en plein écran. Okay, thanks for coming. Yeah, I would like to talk about an optimization that I've been working on in the past couple months. This follows a presentation I did at DEF CON. So yeah, it's about how to use WASM precompiles to try to reduce part of the state of like an ETH1 chain. Okay, so yeah, as a quick reminder, the state is mostly made of blocks of accounts, and the accounts have the classical thing, nonce, balance, code, and the data storage. So that data storage is stored as a hash of a tree. And of course, you have the receipts and the indices, which also make for a lot of the actual space. So as a quick reminder, it's less colorful than what EthCC did, but I'm sure a lot of you had plenty of time to know how to find out how the account try works. So I'm just going to focus on the account, and you can see you have the storage root here. And if you want to expand that the way EthCC said he was doing it, actually, this is what you get. So it's just completely hypothetical, but you can see it gets very, very big very quickly. So if you perform a sync, like a fresh sync, this one dates from last Sunday, you can run this command get inspect on it, and you can see that well, most of the state is indeed made of headers of bodies. But the try nodes, it's starting to get pretty big as well. And there's the receipts as well, who are kind of something that would be nice to get rid of in the future. But yeah, so far they're being kept. So yeah, there's this problem in economics that I'm sure is well known. It's called the tragedy of the commons. And in this problem, the state effectively comes as a bargain. Because yes, you pay some gas to store some data, but the current promise in the protocol is that it will be there forever. And because it's there forever, dividing any cost by infinity is still zero. So it's you just store and you forget about your data. And however, if you are someone working working a full node, maintaining a full node, you have to keep that data forever. So yeah, that's the problem. There's no you already have efforts trying to address state scalability. You of course have stateless clients. You've heard about that for the last 2 hours. The thing is, the biggest problem I see with this approach, even though it is necessary because you want to be able to access Ethereum from your mobile phone, you still need to rely on full nodes. You need full nodes to still be around to produce proofs so that you can get the data you need, get the proof that this is actually necessary. And yes, someone will have to do this. This is going to come at a cost, and less and less people are going to be incentivized to provide this. So you will have, I mean, at least there's a risk of having some centralization. And of course, in long term, you have ETH2. But it's not quite clear yet how the ETH1 shard, which will be part of the whole system, is going to be handled. And because of that, there's still merit in trying to keep the state as small as possible. So what I'm looking for is just a short-term method to keep the state, to reduce the state, to make it less of a burden as possible. And yeah, so the basic solution to the problem of the tragedy of the common is to privatize the commons. So in that case, you privatize parts of the state. It becomes somebody's responsibility. For example, if you're CryptoKitty, you can't be dumping cats all over the place. It's your cat. You take care of it. And so yeah, the idea is to take something out of the main chain, what the node is, what the full nodes are handling, and move it to let's say more of a community approach, where if you are part of the CryptoKitty community, well, you are collectively responsible for handling the state, and only the root will be saved on on the chain. So this is the current. This is a simplified version of how the current system works. You have the chain here, and the chain points to the root hash of the tree. And so in blue, this is the account tree. And yes, the account points to a root, and the root is so the first dApp has its own root, and they have the tree underneath. And same thing with the second. Well, in this approach, you only maintain the root, and everything, like you need a special node to actually take care of the state for you. So if you're a CryptoKitty, you will have to run your own nodes. If you're anybody else, if you have an ERC20, well, at least you have an explanation for at least a justification, an economic justification for the existence of your token. So the advantages of this approach, well, it's that it can basically be implemented right now. You cannot really hack, like get the state root, but you can just have a state of just 32 bytes to hold the hash. So you have like a very simple tree that contains the root of an off-chain tree. And then you can start experimenting with every change you want, like there are currently being discussed for Stateless and for ETH2. So if you want to use binary trees, if you want to use fancy signature schemes, you can. And if you want to go the other way, if your state is only, or your storage is only 1 bit, well, why do you need a tree, right? You can just store that bit in the 32-byte reserved for the hash. And yeah, what's nice is that you can it will affect full nodes, so it will be a way for full nodes to reduce their sizes. Of course, that wouldn't need a fork. That part would need a fork. You would be able to reclaim, to garbage collect, literally garbage collect all those cats. But yeah, it could be done fairly easily. And yeah, the last advantage is indeed that I'm not pretending to come up with any new idea. It's already being discussed for ETH2. So doing this thing can be done on a per contract basis and pave the way for whatever ETH2 execution engine turn out to be. So I come up with a very simple model here. It's not a functional one, but it's just to explain the way things would work. So you know, it's like an ERC20, except instead of having a map with a list of accounts and their balances, and instead of having a function like transfer thing and things like that, you just reproduce, you use the storage tree or the storage trie as the token account trie. And you can use a binary trie, why not? Sorry, binary tree. And yes, you have this model which is balance nonce signature, and you just pass like token transactions, which are effectively layer 2 transactions. You pass them. You don't even need to persist them on chain before you actually before you really need to, before you detect there's a problem with the way people are dealing with you. So in practice, this is I realize I forgot to add the signature here, but this is like a traditional Ethereum transaction. You have a data field, and in the data field you have the proof and the list of transactions, and those transactions are layer 2. They are represented here, so just the nonce, the value from 2. And because it's a model inspired from ERC20, you don't even need the signature here, because the signature from the sender address has to be the same as the one here, so it will be validated. Once again, the field is missing. Sorry for that, but it should be here. So the way the algorithm works, well, you just check the proof, and then you apply transactions one by one, and at the end you recalculate the updated account trie, and you put the hash back into the contract storage. So yeah, just going through the steps. You start from the root. You start from the root. You use the proof to rebuild the trie that has just the recipient state and the sender state. You just verify. You do the usual verification, so signature, and you check that the balance is correct. Then you just transfer the balance from one account to the next, and you recalculate the hash, and that's updated. Yeah, so one remark that is fairly important, there's a double spend possibility in that model. It's just an example. Because there's a nonce. Okay, thanks. There's a nonce. And if I want to give the nonce, if I want to, for example, if I give someone a transaction that has the nonce, they can check that at the time I give it to them, the nonce is the correct one. But then when I see they publish it on they embed it in an ETH1 transaction and they publish it on the network, I can craft my own transaction that will have a higher gas price, and therefore my transaction will go first. And by the time it gets to their transaction, the proof will be invalid, so they will be rejected. But you still have a lot of nice things. You can pack several transactions for the same proof. So in the same ETH1 transactions, you can pack several token transactions. That's because the proof, in that case, like you need to spend gas for the length of the transaction. But if you all start from, if you have one starting point, the same starting point, and then each transaction is applied in sequence, you don't need to save the intermediate proofs. You don't need to pack them and reuse them and unpack everything. So you can just share the cost basically between several people. And at this stage, we're effectively just like a state channel system. But yeah, with a big bug. Yes, it's the problem. I already alluded to it when I spoke about double spans. The thing is, you need to have a hash that's going to be up to date. So if you have a low bandwidth application, if there's no kitty craze and you're the only one in your block, you will go through. Otherwise, you need to use for something that in ETH2 parlance is called a relayer. So it's some kind of node that you give your transaction to, and they will package it for you. They will create the proof. They will collect, like gather all the transactions. They will embed them in one ETH1 transaction. They will create the proof for that. So just to extract all the needed accounts. And of course, they usually do that for a fee, presumably paid in the ERC token itself. And yeah, you can do that, and this is already something that is pretty much very close to what ETH2 is planning to do. So implementing all that could be done right now, except yeah, EVM code is a bit too expensive for that. Or so this is where precompiles come in. So the way instructions are priced, they're priced for any task possible. So usually the way the price got decided was by running a lot of code and trying to see what the average price is. But in the case of precompiles, you know what this is for, so you can try to pay for just the task. So based on the input, you know how much running this specific algorithm is going to cost you. And in that case, we spend our time rebuilding the try and hashing the try, so it's going to be very very repetitive. And if you implement it in you know, as a precompile, you have plenty of options of optimization options like caching, like parallelizing if you want. That is not so easy to access from the EVM. Why WASM? Because that was in the title. Well, there's been a lot of pushback. Trying to add a new precompiles introduces a risk of breaking consensus, because every single client implementer has to re-implement it in their own language. It's you know, it's risky if there are differences, if there are disagreements, if there are debates. So usually, historically, it's been very hard to add precompiles. So WASM is like a blob that can be something that is interpreted by a virtual machine. And because of thanks to that, you can just add a virtual machine interpreter to your an interpreter to your client, and you can drop the blob, and you need to do the validation once, and you know everybody will behave the same. And then you're free to do optimize, like optimize it, rewrite it in your native code, but you have something to compare against. All right, I'm running out of time, so there used to be some improvements that Yoichi Hirai and I worked on to basically it's improving the previous model by adding smart contracts, and you can solve the double spend problem. But yes, so it's I have to skip it, and I will point you to these repositories that do implement part of it. I call it. Oh yeah, I forgot to say I call this this project Jupiter because it's a shameless copy of Raiden, which is a god of thunder. So I say, why not name it after a god of thunder that is also a shameless copy of a Greek god of thunder. And yes, that's pretty much it.
Okay, we can do one question, but only one. So maybe. Okay.
How do I spell my name? Yeah.
So thank you very much, Guillaume, and. Souvent, il y en a qui ont soit qui n'ont pas l'ordi, soit tu mets ça sur l'ordi, ça marche pas. Alors si tu mets ça sur l'ordi, en fait, tu vas juste dans le dossier, c'est comme une clé USB, et tu cliques dessus, tu cliques sur ça, ça le lance. En fait, dès que ça arrête de clignoter blanc, ça se met juste blanc normal. Tu cliques dessus et ça display. Okay. Là, on n'a pas de Mac. Ah non, malheureusement. Du coup, c'est ça, il faut envoyer sur une adresse spécifique. Alors, c'est celle-là. Donc en gros, ils envoient sur ça, tu refresh, et ensuite ça arrive. Il vaut mieux qu'ils envoient un lien, parce que à chaque fois, quand ils envoient quelque chose, malheureusement, il n'y a pas de... voilà, il n'y a pas de message. Voilà, ensuite, donc quand il y a une question, tu vas donner le micro, voilà, et... Voilà, surveille bien le temps, et si tu veux le display, tu appuies, ça devient rouge, et si tu veux l'enlever, tu vas appuyer, ça devient voilà. Tu restes appuyé, c'est ça? Ouais, tu appuies une fois juste, et ça devient, regarde, hop. Et là, je l'enlève, hop. Et normalement, le prochain... C'est sûr. Ouais. Excuse me, Silur is here or not? No. Okay. Merci. Je suis désolé parce que il est pas venu du coup. Ouais, bah je sais que il faudra appeler. Expliquer ce que tu voulais. Ouais, suffisamment. J'ai vu Jupiter à la fin, au moins tu auras pu le caler. Voilà, c'est ça. Ouais, j'espère. Ouais. Voilà. J'espère que les gens suivront un peu, histoire qu'on sauve le réseau. Mais bon, ouais. On verra bien. Bon, ben, continue en tout cas. Ouais, merci. C'est encourageant. Tu t'appelles comment Valentin. Valentin, très bien, ouais. Valentin. Je suis à CryptoSphere, tu peux ce que c'est? Non, pas du tout. C'est la première association étudiante blockchain qui est née en France. D'accord. À Rennes, Paris, ouais. Donc, ouais, c'est ça. D'accord, et pas à Lyon? Si, justement, on a ouvert une antenne à Lyon. Eh ben écoute, je suis à Lyon la semaine prochaine. Ok. Si tu peux me mettre en contact avec les gens. Tu sais quoi, on va faire on est en train de lancer un hackathon. Ouais. Un hackathon blockchain, donc avant tout sur la santé. Ouais. Et, sur la santé, d'accord. C'est ça. Sur donc blockchain santé. Rousseau, c'est un nom intéressant. Ouais. et du coup, tu peux me contacter, je te mettrai en relation. S'il te plaît, d'accord, je fais ça, ouais. Oui, parce que moi je suis lyonnais à la base, donc ça m'arrive de retourner et j'essaie un peu de développer l'écosystème là-bas, sachant que... Ouais, en fait, ils se sont rendus compte qu'il y avait énormément d'organismes de santé implémenter des solutions dans la blockchain.
Ah bah, ce serait génial.
Ouais. Du coup, je te mets en relation avec eux et
Oui,
tu comprends.
cool. Ouais, comme ça, tu peux aller leur parler. Bon,
Ouais.
encore une fois, je suis là toute la semaine prochaine.
Ça
Je suis
marche.
là-bas toute la semaine prochaine.
Ok, bon,
Cool.
très bonne journée à toi.
Eh ben, de même, merci.